Hi everyone, welcome back. So today in this video I will be discussing an interesting problem from CSES problem set. The problem goes by the name coin collector and it comes under the topic of graph algorithms. This problem utilizes the concept of strongly connected components along with dynamic programming. I will explain how these two concepts will be used together in this question. So let's get started. So the problem reads like this, that a game has n rooms and m tunnels between them. So we have n rooms and m tunnels. Each room has a certain number of coins. So every room is associated with some number of coins. What is the maximum number of coins you can collect while moving through the tunnels when you can freely choose your starting and ending room? So in input we would be given n and m and then n integers that will be representing the number of coins present in each room. Then there will be finally m lines describing the tunnels. Each line has two integers a and b, that is a tunnel will be present from room A to room B, and each tunnel will be a one-way tunnel. That is, if a tunnel is directed from A to B, then it means that we can only go from A to B and not from B to A. So it will be a directed one. In output we have to print one integer which will represent the maximum number of coins we can collect. So if we consider the given example, so let me explain you on the board. So we are given with this example in which the value of n is 4 and m is also 4. So there are 4 rooms. Consider it like this: first room, second room, third room, fourth room. The coins present in the first room is equal to 4. The number of coins present in second room is 5. In third room it is 2, and in fourth room it is equal to 7. So these are nothing but the total number of coins that are present in each of the room, and then we are given with m lines. So let me draw the given graph. So as I said that the number of coins present in each room are given through this array. So 4, 5, 2, 7. So here 4, here 5, here 2, and here 7. So the question has asked us to find the maximum number of coins we can collect while moving through the tunnels when you can freely choose your starting and ending room. So if we start from the first room, then we will be collecting the coins in the following order. So we started from the first room, so we will collect every coin that is present in this room. So in the first room total 4 coins are present, so we will be adding 4 to our result. And then we have two options to go from this first room, that is, from one we can either go to this second room or we can either go to the third room. So suppose we go to the third room. So if we go to the third room, then we reach third room, and then we will be collecting every coin present in the third room, which is 2. So we will be adding 2 to our result. So after this, from this third room, it is not possible to go to any other room, so we will stop here. So how many coins we collected? We collected a total of 4 plus 2, that is 6 coins. Now suppose if we have decided to go to the second room instead of third room, then the coin that will have been added to our result will be 5, right? Now is there any way to go from the second room? Yes. From second room we can go either to the first room back or to the fourth room. So suppose we decided to go to the fourth room. So if we went to the fourth room, then the coin value that will be adding to our result will be 7, right? And now if you see that it is not possible to go anywhere from the fourth room, so we will stop here. So how many coins we collected? So we collected a total of 16 coins. Suppose we have decided to go from 1 to 2 and then again 1 and then 3, right? Like this, from 1 to 2, then 2 to 1, and then 1 to 3. So in this path, how many coins will have been collected? So we will be getting 4 plus 5, and since we have already collected 4, then we will not be collecting that again. Then we went to 3, that is 2. So total coins that is present now is 11. But what if we have started from the third room? So if we have started from the third room, then the total number of coins that we would have been able to collect would be 2 only, because from here we would not be able to move anywhere, right? So if we have started from the first room, then the maximum amount of coin that we were able to collect was 16. If we started from the third room, then the maximum number of coins that we would be able to collect is 2. Similarly, if we started from the fourth room, then again we will not be able to go to any other room, so the maximum amount of coins that we will be able to collect is 7. And if we have started from the second room, so if we have started from the second room, so we would be collecting these 5 coins. Then through this path we would have moved to the first room and collected the another 4 coins. Then from this path we again come back to 2 and then go to 4 and collecting the remaining 7. So again the total number of coins that we would have collected would be 16, right? Since in the question it is mentioned that we can start from any given room and go to any particular room if possible, so that's why we started from either first room or second room, and the maximum amount of coins that we were able to get is 16. So answer for this question was 16, right? Now consider this example. This might look little complex, but I will explain you, don't worry. And these represent nothing but the coin values that are associated with each room. So suppose we have started from the first room. So if we start from the first room, then what will happen? See. So if we start from the first room, then from first room we can go to the second, from second we can go to the fifth, from fifth we can go to the sixth, then sixth we can go to the 2, and then 2 we will again come back to 5, then from 5 we will again go to 3. So if we start from the first room, then in total we would be able to visit these much nodes at least, right? So we would be able to visit these much nodes. So the total number of coins that we would have collected in this case would be 9 plus 8 plus 7 plus 6 plus 5, right? Now suppose we collected this 5 coins from the fifth room at last, then we decided to move to this ninth room through this edge. So if we have moved to the ninth room, then we would be adding 1 coin more of this room, and from ninth room we decided to go to the fourth room, so we would have added the second, that is 2 coins. So now the total number of coins will be 3 more, that is 38. And if you see, then we would have covered these much number of nodes in total, and we can't go further to any other node. Like we cannot go from this component to this node, or from this component to this node, or from this component to this node. But since there was an edge from this node to this node, that's why we were able to go from this part to this part, and we were able to collect the coins present in this component also, right? So we got 38 when we started from this component, that is this node. What if we had started our coin collection from the 0th room? So if we have started from the 0th room, what if we have started our coin collection from the 0th room? So if we have started our coin collection from the 0th room, then suppose from the 0th room we go to the second room, from 7th room, sorry, and then from the 7th room we went to the 8th room, and from 8th room we had 2 choices, that is we can either go to the 6th room or the 9th room. So suppose I decided to go to the 6th room, then as soon as I entered this component, that is this node, we saw that we would be able to visit each and every node of this component if we reach any one of these nodes. So the total number of coins we would have been collecting in this case would be 4 plus 3 plus 2 plus whatever number of coins was present in this component. So it was 9 plus 8 plus 7 plus 6 plus 5. And after we have collected coins from this component, suppose we are at this node at the end, then through this edge we could have moved to this component as well. So we would be collecting the remaining 1 plus 2 coins. So in this way we were able to collect each and every coin present in this graph when we decided to move from 0 to 7, then from 7 to 8, then from 8 to 6, and then from 6 to 2, 2 to 5, 5 to 6, 6 to 2 again, 2 to 1, 1 to 2, 2 to 5, 5 to 3, then 3 to 4, 4 to 9. So in this way we were able to collect each and every coin present in this graph. So the total number of coins we collected in this case was 47, right? So 47 is the maximum amount of coins that can have been collected if we started from 0 and moved through the edges that I just told. So 47 will be our answer for this case. So if you see carefully, then this can be regarded as a separate component basis on some property. I will tell you what property. Similarly, this will be a separate component in itself. Similarly, this, and then this. So what common property these 4 components hold together? So you can notice one thing, that in this component it is possible to reach any node from any other node. Like if we select any two pairs like 1 2 or 1 3 or 1 6 or 1 5 or 2 3 2 6 2 5, any two pairs, then it will be possible to reach any node from any other node in this part of this graph. So that's why we are regarding this as a separate component. And if you know the concept of a strongly connected component, then it is regarded as an SCC, that is an strongly connected component. That is a strongly connected component, right? Similarly, this is also an independent strongly connected component, this is also an independent strongly connected component, and this is also an independent strongly connected component. So what is the concept of a strongly connected component? It just want one condition, that is in this part of the graph any two nodes will be reachable to each other. That is, if we are able to go from 1 to 5 through some path, then it should also be possible to go from 5 to 1 via some other path, right? So this is the condition of a strongly connected component. So you can verify that each of these 4 components are independent and strongly connected, that is any two nodes will be reachable from each other. So if you just see why we did not included this 0 in this component, because you see we can go from 0 to 7, then from 7 to 8, then from 8 to 6, and since we entered this component, it means that from 6 we can reach any other node, so we would also be able to reach 1. So from 0 we can reach 1, but if you try to find any path, then you will realize that you will not find any path that will lead from 1 to 0. So we can go from 0 to 1 but not from 1 to 0. That's why 0 is not a part of this component. That's why it is present in a separate other component. And moreover, let me tell you one more thing, that we can treat this separate component of the graph, that is the strongly connected component SCC, as a separate node. So if I consider this component as a separate node, then what graph we will be getting? See, so this will behave as an independent node, so this will be an independent node, these 3 will also be 3 independent nodes, right? And the connections that are present are like this. From this component the edge is going from here to here, that is this. From this component to this component, that is this. From this component to this component, like this. Here it's like this. And from this component to this component, it's like this. Now since we have condensed each of this component in the form of a separate individual node, so this is called as a condensation graph or the condensed graph of this given bigger graph, right? So this is called as nothing but a condensed graph. So this is a condensed graph, right? And if you notice one more thing, then you will realize that this condensed graph will always be acyclic. So this condensed graph will always be acyclic in nature. Okay, and what will be the value of these nodes? So for now I am giving it like regular indexing, that is 0, 1, 2, 3. So we saw what is a SCC, that is a strongly connected component, and how we can obtain a condensed graph from the collection of these SCCs, right? And we also saw that this condensed graph will always be an acyclic in nature. So I hope that you know the concept of Tarjan's algorithm or Kosa-Rajou's algorithm, like how we can use these algorithms to obtain the strongly connected component graph, right? And once we have obtained this strongly connected component graph, we would also be able to get this condensed graph. And using this, we will also be deriving our final answer. So we will see how this concept of a strongly connected component fits perfectly in this question. So let me give you a brief explanation of how the Kosa-Rajou's algorithm work. So if you know, then what we do in the first step, we use the concept of timeout in order to find the order of nodes which will be visited during the backtracking, and we will be storing those order of nodes in a data structure, say stack. So if we start our DFS call from 0, then during backtracking our stack st will be storing the nodes in the following order, that is first 7, then 6, then 5, then 4, then 3, then 2, then 1, then 0. So it went like this, like 0 to 1, then 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7. That's why during backtracking it filled like 7, 6, 5, 4, 3, 2, 1, 0. So this will be our stack. So after doing this first step, what we do next in Kosa-Rajou's algorithm? So we simply reverse the graph. What do we mean by reversing the graph? I mean that we simply have to reverse every edge present in this graph. Why? Because it will help us to prevent going from one separate component to other component. Like if you see for now, then this is in itself a strongly connected component, but it is also possible to go from 2 to 3, but not from 3 to 2. That's why 3 is not a part of this component. But during the DFS call, we will be going from 2 to 3 and will not be able to come back. So we don't want that. That's why I want you to reverse each and every edge present in this component. So let me now draw the graph after reversing every edge. Now the reversed graph looks like this. And now if you see, then this is a strongly connected component even now. And if we start our DFS call from 0, then we will be visiting 0 to 2, then to 1, and we will not be able to go to this separate component, like, right? So this was a helpful thing by reversing each and every edge. This was also a separate component, and this is also a separate component. So in total there are 4 separate components here. So we discussed the second step of Kosa-Rajou's algorithm, that is reversing each and every edge. And what is the next step or the last step in Kosa-Rajou's algorithm? So the next step in Kosa-Rajou's algorithm is to stop our DFS call from the top of this stack and start visiting each and every node that this node can visit, right? So here the top of the stack contains 0, so we will start our DFS call from 0. So if you start our DFS call from 0, then from 0 we can go to 2, then from 2 we will be going to 1, and then again to 0, right? So when we started from 0, we visited 0, 1 and 2. So we visited 0, 1, 2, and now the top of the stack contains 3, so we will start our DFS call from 3. So when we started our DFS call from 3, we will only be able to visit 3 only, because it is not possible to go from 3 to anywhere, and even if it is possible, it is already visited, so we will not go to that part. So from 3 we can only go to 3, and then the top of the stack contains 4. After starting the DFS call from 4, we can go from 4 to 6, then from 6 to 5, then from 5 to 4, right? So by starting from 4, we will be visiting 4, 5, 6. So 4, 5, 6 is visited now too, and then the last element present at the top of the stack is 7. After starting the DFS call, we would only be able to visit 7, right? So in this way we visited each and every node present in this graph using the Kosa-Rajo's algorithm. And what is the number of times we have to start our DFS call? So we started our DFS call in total 4 times, like from 0, then from 3, then from 4, then from 7. So total number of calls that we did for DFS is 4. So we can say that the total number of strongly connected components present in this graph is 4. And the first component contains 0, 1, 2, the second component contains 3 only, the third component contains 4, 5, 6, and the fourth component contains 7. So this was all about Kosa-Rajo's algorithm, how we can find the total number of strongly connected components and what nodes that each component will hold. So let's now come back to the question. So in the given question, the example given in the input was this, and in this example it is clearly visible that there are 3 components. It is this component, and this component. So we do not need to worry about all the nodes. Like if we know that we are starting from this first room, then we also know that if this 1 and 2 are present in the same component, then we will also be able to visit this 2, right? That is, we will also be able to collect each and every coin present in this component. This is the main concept present here. So if we started from the first room, then whatever nodes are present along with this one in this component as a strongly connected component, we will also be able to visit those nodes also, or those rooms rather also. And after collecting the coins from this component, we had 2 options, like we can have either moved to this component or we can have either moved to this component, that is the third room or the fourth room, either. So after collecting the 9 coins from this component, we had 2 options, like we can move from this component to this third room and collecting the remaining 2 coins, or we can either move from the first component to the fourth room and collecting the remaining 7 coins. So this gave us 11 and this gave us 16. So out of this, 16 was maximum than 11, so this was our answer, right? So what we did in this example, we simply broke down the given directed graph into form of several connected components, right? So we got 3. So using the Kosa-Rajo's algorithm, we can obtain these 3 components, and we would be knowing that there exist 3 strongly connected components, and the value of the nodes present in this component, that is the first component will be containing 1, 2, the second component will be containing 3, and the third component will be containing 4. And the coin values associated with each node is already given in the input, so we don't need to worry about that. We will utilize this later. But what if our given graph was pretty large? Like if you see in the given example input, then this graph is fairly small, and you will probably wonder why dynamic programming should be implemented here. I understand that, but just consider that if the given graph was very large. So if the given graph was very large, so there would have been multiple components, right? There would have been multiple components, and each of the component would have been containing some nodes, and each node was containing some coins. So suppose this component has contained a total of X coins, Y coins, Z coins, A coins, B, C, F, G coins, right? In the question, if you see what has been asked, so it has asked us to find the maximum number of coins we can collect while moving through the tunnels, right? So we have to maximize the number of coins while moving through the tunnels. So we are not sure that from which room we should start. So we can either start from this room, or rather this component, or from this component, or from this component. So we can start from any component, we are not sure. So we have to check out all the possibilities, right? Let me convert this condensed graph in the form of DAG, that is directed acyclic graph, to make you understand better. And let me also associate these individual SCCs with some coin values. So suppose these nodes represent the coin values that are present in this component. So if 8 is present here in this node, it means that the whatever the total number of nodes were present in this separate SCC, the sum of coins would have been 8. Similarly for this would have been 4, and so on for every SCC. So suppose we have started our journey to collect coins from this component, that is the component that contains a total of 8 coins. So how many coins we would be able to collect at maximum if we started from this component? So here 8, and then from 8 we would have moved to 4. From this 4 we would have went to 6. Then from 6 we went to 1. Then from 1 we would not be able to visit anywhere. So I think instead of visiting this one, what we can do is from 6 we would have moved to 2 instead of 1. So if we have moved to 2, we would be collecting 2 coins. Then so let me also mark the nodes which we are visiting. And after this 2, suppose we move to the 7, and then from 7 we move to 5, and then from 5 we move to 3. So in total we have visited these much of the nodes. So we visited almost all the nodes except this node. So what is the maximum number of coins that we were able to collect? We were able to collect a total of 35 coins. And I think this is the maximum amount of coins that we can collect. So the answer for this example would be 35, I believe. But what if we have started from any other node? So was our answer would be greater than or equal to 35 or less than 35 in that case? Let's see. So we got our maximum answer when we started from this component, right? That is the component that was containing a total of 8 coins. So in a more bigger and complex graph, we will not be sure like from which component we should start. So we will be trying every possibility, like we would be starting from each and every component and seeing what is the maximum amount of coins that we can collect. And since we saw that after reaching from 8 to 4, then from 4 to 6, and after 6 we had two possibilities, like from 6 we can have either went to 2 or to 1, but we decided to go from 6 to 2 and not to 1, right? So there are multiple possibilities, and whenever the possibilities come, we use the concept of dynamic programming. That's why here dynamic programming will be used, and it will be a very simple recurrence relation. It won't be very complex, so you don't need to worry about that, right? And as I told you that we have to start checking and maximizing our answer from each and every component. So suppose there are n components, right? Suppose there are n components and we have to maximize our answer by starting from each component. And suppose our final answer would be stored in a variable called res, that is result. So res will be equal to maximum of result comma whatever the result obtained when we started our search from this ith component, right? And what does this obtain function will return? It will return us the maximum amount of coins that we can collect when we have started from this ith component. So suppose the value of I is 8 here. So we saw that when we started from the 8th room, then we were able to collect a total of maximum 35 coins except this coin, right? So this function would have returned 35, and hence the maximum value of result would be 35 only. So we will have printed that. So the function of this obtain function is to return the maximum number of coins possible by starting from this ith component or the ith node in this condensed graph, right? How will this obtain function look like? So it will be like this. We know that when we have called for I equal to 8, then we will be collecting the 8 coins, right? So the function has to return like 8 coins at least, plus whatever the maximum amount of coins it was able to get, from its neighbors, right? Right? So we just have to take the current amount of coins that is from this component and whatever the maximum amount of coins it was able to get from its neighbors. And for more bigger and bigger graphs, there will be repeating sub problems. So in order to calculating again and again for those sub problems, we will be using dynamic programming here. So we will be storing this we will be storing this value in a DP table, and it will be 1D array only. And before returning, we will just check if this have been previously seen or not. If it has been seen, then we will simply return from here. Nothing complex. So I hope you understood. So let me explain you from the beginning what has happened, because I believe it might have got little complex, but you don't need to worry because everything is so simple. So in the question we were given n rooms and m tunnels. So this was the given graph, and we were allowed to start from any node, so we can have started from any other node. And each room was associated with some coin values. So the first room was associated with 4 coins, second room with 5 coins, third room with 2 coins, and fourth room with 7 coins. So each room was associated with some coin values. And what our work was there, our work was to collect these coins while visiting these nodes. So I told you that using the Kosa-Raj's algorithm or using the Tarjan's algorithm, you can use any one of them. We will be finding the strongly connected components, like we will be dividing the given graph into strongly connected components. So for this example, there was total of 3 strongly connected component, that is SCCs, and we would also be knowing what nodes are present in each component. And we also noticed one thing, that if you are present at any node in a given component, then it will always be possible to move to any other node, because it is a part of SCC of this component. So if we are at 1, then it means that whatever coins are present in this component, we will be collecting that. So we collected 4 and 5, and then we had options, like we can have moved either to this component, that is the third room, or we can have either moved to the fourth component, that is the fourth room. So there were multiple possibilities, and suppose there were more components, like from 3 there were further other components, and like from 4 there were other components too. So a large number of possibilities would have been occurred, like we can have went from the first component to the second, from the first component to the second component, then from the second to the third, right? Or we can have moved from the first to the second, then from second to the fourth, or we can have moved from the first to the this component, say fifth component, and then from fifth to the fourth. So there were multiple possibilities. That's why dynamic programming was helpful here in this case. So after getting the condensed graph, each node will be representing a separate component. So for this example, there were 3 SCCs, so the condensed graph would have contained 3 nodes only, and each node would be representing the total number of coins that was present in this component. So suppose this was some given example, I'm not taking the actual example. So the condensed graph was this. We wanted to maximize our answer, and we saw that there were multiple possibilities, so we really didn't have any choice. So we have to start checking from each and every component in this condensed graph. That's why I did this. I just maximized the value into the result variable. And suppose I started from this component, ith component, right? So when I started from the ith component, then what does this function will have returned? So since I have started from the ith component, then the function will be returning the total coins present in this ith component plus whatever the maximum amount of coins it was able to get through its neighbors, right? Simple thing, simple recurrence relation. And I just memoized it, like this is a small graph, so we will not be able to see multiple sub problems, repeating sub problems. But if the graph was larger, then there would be definitely repeating sub problems. So for that I just memoized this in a 1D array. And if this state has been previously visited in the DP array, we would be returning that value without further calculating it. So that's why dynamic programming was used here. So I hope you understood the logic part, like why strongly connected component and Kosa-Raj's algorithm. Through this example, I tried to make you understand the concept of a strongly connected component and how it is obtained using the Kosa-Raj's algorithm. After it is obtained, I tried to explain you how a condensed graph is obtained after this, and why a condensed graph is always acyclic. After the condensed graph is obtained, I explained you how we can utilize this condensed graph and the concept of dynamic programming together through a simple recurrence relation in order to obtain our maximum number of coins. So this was all about this problem. So let's now come to the coding part and quickly solve this up. So in the input, we are asked to take the inputs of n and m. So n and M representing number of rooms and the number of tunnels. Then we are required to take the input of coins associated with each room. So I'll be storing those coins values in a vector, and I'll be using one based indexing, right? So initially the coin values associated with each room is 0. So for n rooms I have to take the input. Better I should start from 1, I guess. So after the input for the coins has been done, I want to take the input of the M tunnels. So there will be a directed edge from U to V, and I will be storing this in an adjacency list. After this has been done, and one more thing, I think I should initialize this adjacency list. So it will be like this, and its size will also be n+1. So I'll be using one based indexing here also, right? After this, what I told you to apply Kosa-Raju's algorithm in order to obtain the strongly connected component graph. So for that, we know we have to store the timeout nodes in a data structure. So I will be using stack. You can also use vector, but I will be using stack. So here, and I will also be using a visited array, right? And it will also be one based indexing only. Initially every node is unvisited, that is every room is unvisited. Then after that I will start my DFS call in order to fill the stack, right? So it will be like this, and if this current room is not visited, then I will start my DFS call through this room, and I will be passing the stack, and I will also be passing the adjacency list as parameters, right? After this is done, I think I should write the DFS function here. So what parameters I passed the node, current node, or say room. So this is the room, and then I passed stack, and don't forget to pass it through reference, other copies will be made, and then the adjacency list, right? This will be a closing bracket and not dot. And one more thing, I think I should have passed the visited array also here. So just like this, also pass it through reference only, and then I will be just doing the simple DFS, that is visiting this room, that is marking this room as visited, and then iterating through its neighbor nodes in the adjacency list. And if this adjacent neighbor is not visited, then I will be calling the DFS function through this adjacent node, right? And while backtracking, I told you to store this current room in the stack. So I'll be pushing this room value in the stack. So the main function of this DFS call was to ensure that the stack is filled in the order of timeout, right? That is the order of backtracking. So our stack is now filled, and after this has been done, what is our next task? I told you that we have to reverse each and every edge present in this graph. So in order to reverse the edge, what we will do, we will be constructing another adjacency list. Let's name it like adjacency list reverse, and its size will also be the same, that is n+1. And how will I do this? So we would be visiting each and every room, and whatever the nodes was earlier present here, that is whatever the neighbors were present there, that is this. So this IT represents the room through which the eye was connected before. So now since we have to reverse the edges, so adjacency list reverse dot adjacency list reverse of this IT, right, dot pushback I. So in this way the reverse adjacency list will be constructed. After this is done, I told you that we have to start popping the elements from the top of the stack and starting the DFS call, right? So we will be doing the same exact thing here. So while our stack is not empty, the top element, let's name it IT, it will be st.top, pop it also, and through this IT what I will be doing, I will be just checking if this is already visited or not. So if this is already visited, so we won't start DFS call again, right, because it is already visited. So I will write continue, but if it is not visited, then I will start a DFS call, and it will be of another type, like it will not be the same as this DFS call, because in this DFS call I was filling the stack, but now I don't have to fill the stack. So let's name this DFS call as DFS2, right? And what parameters I will be passing? I will be passing this IT, I will be passing this adjacency list, I will be passing this adjacency list reverse, and we will see what more parameters should we pass. So let me copy down this DFS because it will be the exact same thing. I just need to change the name, and there is no need of a stack anymore. So just erase this part, right? And since it's adjacency list reverse, so let me name this also the same way, right? And one more thing to notice, that when we called the DFS function for the first time, then we visited each and every node. So before calling this DFS2, make sure that each and every node is unvisited again. So just here do this visited I equal to 0, so it will unmark this automatically, right? And we will be passing the visited here. After this DFS2 function returns, so whatever number of times this DFS2 function will be called, it means that those number of SCCs are present in the graph. So I will increase the count of number of SCCs by 1, right? Let me initialize it here. Number of SCC present initially is 0. So after each DFS2 call, I will be incrementing it by 1. And also, in order to store the nodes that are present in each SCC, like in this SCC 0, 1 and 2 are present, in this SCC 4, 5 and 6 are present. So in order to store these also, what we'll be doing, we'll be storing this in a vector. Let's name it component because it represents a component, right? And I will also be passing this component here. So let me copy this up quickly, and I will be passing through it reference only. And while visiting, I will be storing this room, right, in the component. After this has been done, after this DFS2 function returns, the component will be storing each and every node present in a separate SCC, right? And at the same time, what we can do, that for each component, whatever the total number of coins are present in each component, we will be also calculating it at the same time, right? So in order to do this, like we know, for each component initially the sum will be 0, initially sum will be 0. What we can do is we can iterate through each and every element that is present in this component and increment our sum to whatever the value associated with this room in the coins array that we just took the input here, right? So that's why sum equal to sum plus coins of IT. So this will store the total amount of coins that is present in a given component, right? And let me store this sum in a separate vector, say component sum. So component sum dot pushback this sum, right? Let me declare this component sum here. So vector of int component sum, and it is zero based indexing. You will realize soon why I have used zero based indexing for this component sum. And I also told you that we have to derive condensed graph from this given graph, right? That is from this SCC group of SCCs we have to derive the condensed graph. So how we will derive this condensed graph? So for that, what I will be doing here, I will be initializing a vector, say roots. I will explain very soon how this will help us, and it will be one based indexing. Let's initialize it to 0, right? So when I was calculating the sum of coins for each component, I will be giving this element of this component. Like for a component there were multiple elements, like if for this example, if you see there are 5 elements, 1 2 3 5 6 for this component. So what I will be doing is that I will be giving this 1 2 3 5 6 with a common ID, say 0. Similarly for this component there are 2 elements, that is 0 and 7. So I will be giving these 2 elements with another ID, say 1. Similarly for this 2, similarly for this 3, right? So let's say it ID and start it with 0. So roots for this ID will be equal to ID only. And when the number of components will increase, that is when we move to the next component, then this ID will also increase, right? After this has been done, we want to construct and build our condensed graph. So we have to make the condensed graph. So how we will build the condensed graph? See, so we converted this graph into this condensed graph, but how we did that? So what we will be doing is we will be visiting each and every node present in this original graph and seeing what are the neighbors present for a particular node. Like for 1, what are the neighbors present? For 1, the neighbors present is 1 itself and 2, right? So 1 and 2 are present in the same component. How we will realize this? We will realize this through these roots, because their ID will be same, right? For both 1 and 2 the ID will be 0. So using that we will be knowing that they belong to the same components. That means that we don't need to draw an edge between them. But suppose our node was this 0. So the neighbors of 0 would have been 7 and 1. So if we have checked the IDs of 0 and 1, then we realize that the ID of 0 was 1 and the ID of this was 0. So the IDs was 0. It means that they were a part of different 2 components. So if this was the case, then we will be directing an edge from this to this. That's why we directed an edge from this to this. Similarly, we'll be doing it for every component, right? So to make this happen, what we will do? We will be visiting each and every room, right? And we would also be going through its neighbors in the adjacency list, original adjacency list, right? Not the reversed one. And just checking if the IDs are different, that is roots of this V, that is the roots of current room, is not equal to the roots of this IT, it means that they belong to two different SCCs. And if they belong to two different SCCs, what we will be doing? We will be directing an edge from this. We'll be directing an edge from this to this. So let's name it as adjacency list condensed, right? So adjacency list condensed. So we directed an edge from 1 to 0, right? So root of this towards root of this, that is roots of V towards roots of this IT. So let me initialize this adjacency condensed list here. So vector of int and I'll be using one based indexing here only. So using this our condensed graph is made, that is this is made, right? And after building the condensed graph, what I told you that we will visit each and every component, that is each and every node present in this condensed graph, and we'll be maximizing our answer by starting from each of the component, that is checking every possibility. And since I have started my ID from 0, so the ID associated with each node in the condensed graph will be from 0 only. So I have to start from 0 in this case. So 0 tell number of SCCs present, right? That's why I incremented the count of number of SCC and tried to find the number of SCC present in this graph. So number of SCC, this. And for each call, what I just wanted to maximize our answer. The rest will be maximum of result comma whatever the DP function returns for this ith component, right? So what parameters will be passing in this DP function? So I'll be passing the current ID, that is I, the component sum, you will soon see Y, and then the condensed adjacency list that we just constructed above, right? And after that, whatever the final result will be there, will be our answer, and we will return after that, right? So let me write this DP function quickly. So it will return an integer type value. I passed the ID of the condensed graph, and then I passed two more things, that is the component sum and the adjacency condensed list. The component sum is in itself a vector, so let me copy that up and pass it through reference only, and also the condensed adjacency list, right? So let me copy this up and also pass it through reference only. After this is done, what I told you, that I have to return what? See, for this ith room, we will be collecting the coins present in this ith room plus whatever the maximum amount of points it was able to derive from its neighbors, right? That is, we have to return at final the amount of coins that is present in the current room, that is this, plus whatever the maximum amount of coins it was able to get from its neighbors. So say it is stored in res, initially it is equal to 0, so we would be iterating through its neighbors and this condensed adjacency list for this ID, and whatever the nodes it is connected to, I just want to maximize our result. So result is equal to maximum of result comma whatever this DP function returns, and in this function I will pass this ID, then the component sum as usual, and then the condensed adjacency list. So this function returns us the maximum amount of coins that we can get when we will be starting from the ith component, right? And we will be maximizing this here also and then printing right here. But I also told you that we will be using the dynamic programming here. So for that I will be initializing a 1D DP array. So let's name it DP. And so what will be the size of this DP array? So if you see carefully, the size of the DP array should be equal to the number of nodes present in this condensed graph, right? So how many nodes will be present in the condensed graph? It will be equal to this number of SCC plus 1. And let me initialize it initially to -1 to everything. And let me pass this DP array here. After returning this, we will just memorize it for this state, that is DP of this ID will be equal to this. And just before returning, I will check if this DP of ID is already visited or not, that is if it is not equal to -1, and if it is not equal to -1, I will simply return out this DP ID. And let me pass this DP here also. So instead of assigning the size for this condensed adjacency list directly here, I assigned it like this. So now I think I have written the complete code. So this is our given input and the required output was 16. So now if I run up this and see what is the output coming here. Great. So we are getting 16 and the expected output was also 16. So I think this should work. So now if I submit this up in the CSES platform itself to verify the correctness. So let me submit this up there. Okay, so we did one small mistake. So the final answer can exceed the int max value also. So I will be converting every integer to long. So just do that. Now I think it should work. I have converted every int to long. And now if I try to submit this up, I think it should work. Okay, so our solution is completely correct and is accepted on the platform, as you can see. So thank you for watching this video. I hope you understood something new. So if you have any doubt, feel free to comment in the comment section. I will read your comments and try to help you out. See you in the next video.